All right, everyone, welcome back. So this is our lecture wrap-up video series, and this video specifically is for lecture number 7. So today was a shortened lecture due to our midterm review, and we only covered sections 5.1 and 5.2 from your book. Basically, the idea here is to give you the first introduction to an operational amplifier, or an op-amp, as we typically abbreviate that. All right. So this is the main, again, schematic that we looked at in class. Just kind of a quick recap, looking at and then we'll look at the transfer characteristic, and then a couple of other minor points I want to just, again, highlight real quick. So again, this is the general schematic describing the terminal voltages of the op-amp as well as the given currents. So again, we'll have the plus and minus of VCC on top and bottom here, and sometimes these we'll see in the future are not necessarily explicitly written out as such, but it's just kind of assumed that there will be a plus and minus source is basically there to power the op-amp itself. So that'll be there. We also pointed out that the VCC minus does not necessarily need to be equal in magnitude to VCC of plus. The only thing we're considering, though, is that the output of our op-amp, as we'll get into based on the transfer characteristic, is going to be limited by whatever my plus and minus VCC values are. So that's the only thing to keep in mind with as far as that goes. And so then our inputs, we have two separate inputs. We have the inverting input here with the minus indicated with the minus sign. We have the non-inverting input shown here with the plus sign. Corresponding voltages for each of those is VP for the non-inverting, VN for the inverting. So again, these potentials at the nodes are all referenced to some given common node, which is typically shown down here, which relates all the VCCs and everything back to the common, as well as the output here. So again, the output coming from the other side of the op-amp here, we have the V0 value here, which is that output potential, again, referenced back down to our common node sitting right down here. We talked about currents and how those again are defined in relationship to the op-amp. Bottom line is all the currents at each node are assumed to be going into the op-amp, okay? And so that's important to keep in mind with IP, IN, IC minus, IC plus for the currents coming from the sources, VCC plus and minus, and then I0 in regards to the output voltage there. Terminal rather. Okay, so we talked about what is the output from an op-amp. So we said, without getting into any details of what an op-amp is, because that's a whole different other class that you'll have to get into, we simply said that based on some given input on your VP and your VN here, you're going to get some output. And so that's what this transfer characteristic is describing. Here on the x-axis, we have the difference in VP and VN. Plotted as the output plotted as a function of VP minus VN, the difference there. So we see that in this region here between VCC over A plus or minus, we have a linear portion of the curve where the output roughly tracks that difference linearly between your two inputs. And then as we get to some point where that difference gets large enough, then we will reach this what's called saturation, right? So we had saturation region, and this is the positive saturation over on this side. Similarly, if you go to a large enough negative difference here between VP and VN, you'll get to the negative saturation on this side, and then this portion of the curve in the middle there was our linear region. So we also talked about how typically in most circuits, especially what we're going to look at, we're typically always working under the assumption that we're working in the linear region. And how did we come up with saying our circuits would be able to do that? We said that in order to keep the op-amp operating in the linear region, we need to have the so-called negative feedback loop happening there. And so that loop was, I'm going to change my markers here, is if we tie the output here back over to my inverting input, that will result in a feedback between, again, this node, the output node, back into my inverting input on the minus side there, and that will allow eventually this difference to remain a very small quantity, which means we're going to remain closer to the origin of this curve here. All right, so another point was talking about, so if we are assuming linear operation, then we're working under two primary constraints. So the first one is, sorry, switching back markers here, is that our input Vn is more or less going to be equivalent to Vp. And this is kind of based on the fact that, again, in order to be operating in a linear region, this difference needs to be a very small quantity, which in relationship to actual values for V sub Vn and Vp, which are more on the order of what your VCC values, which is maybe several volts, the difference in which you're remaining in this region is only very small, in the order of millivolts. So as a kind of a general assumption that we were going to work with in looking at circuits with op amps, we're going to have this constraint that we place, saying specifically that the voltage on our inverting input and our non-inverting input are going to be more or less equivalent. Then the other constraint we had was with relationship to current, in which we said that In equals IP equals 0. So that's saying there is no current flowing into the op amp, which again, we sort of talked about how, without getting into the details of exactly what's inside of the op amp, since that's beyond the scope of this course, suffice it to say that there's a very large resistance or impedance at each of these given terminals that's going to more or less limit to a very small number the amount of current that wants to actually go into the op amp. So again, as a kind of a simplifying condition on the circuits that we're going to look at in the future, we'll simply say that the current is actually equal to 0, and that'll help us get to some general analytical solutions of some specific circuits that we look at. Okay, so that's the general baseline overview that we covered today in this lecture, and next time we'll be getting into some more specific use of op amps in circuits and see how that actually all plays out. As always, stay classy.